morning. Myself Dr. B. Jyothi, working as an assistant professor in the Department of Freshman and BSH in BVRAJ Institute of Technology, Narsapur. Our course name is Applied Physics. Today's topic name is Quantum Free Electron Theory and Fermi-Dirac Distribution Function. So in this quantum free electron theory, this is the outline of my presentation. In this we are going to discuss about the quantum free electron theory, Fermi-Dirac distribution function, Fermi energy. So in this, what is quantum free electron theory? So why we are studying this quantum free electron theory? So in this quantum free electron theory, to overcome the drawback of classical free electron theory, Sommerfeld proposed quantum free electron theory. So we discussed classical free electron theory. So whatever the drawbacks, whatever the demerits from the classical free electron theory, to overcome these drawbacks from the classical free electron theory, Sommerfeld proposed a quantum free electron theory. So according to this theory, so the Sommerfeld treated the electron as a quantum particle. He retains the vital features of a classical free electron theory and included the Pauli's exclusion principle and Fermi-Dirac statistics. So what are the assumptions from the classical free electron theory? The following assumptions from the classical free electron theory. The first assumption is the free electrons in a metal. In the metal can have only discrete energy values. So thus the energies are quantized. So in these electrons in a metal, so the electrons have some discrete energy levels, energy values. So thus the energies are quantized. So the second assumption is the electrons in the metals obey the Pauli's exclusion principles. What is Pauli's exclusion principle? Which says that there cannot be more than 2 electrons in any energy level. So what is third assumption from the quantum free electron theory is the distribution of electrons in various energy levels obey the Fermi-Dirac quantum statistics. And the fourth assumption is free electrons have the same potential energy, where in this the potential energy everywhere within the metal. The fourth assumption from the quantum free electron theory is free electrons have the same potential energy everywhere within the metal. So because the potential energy is due to the ionic core in uniform throughout the metal. So the fifth assumption from the quantum free electron theory is the force of attraction between the electrons and the lattice ions and the force of repulsion between the electrons can be negligible or neglected. So the sixth assumption is the electrons treated as wave-like particles. The electrons treated as a wave-like particles. So these are the assumptions from the quantum free electron theory. So what are the merits from the quantum free electron theory? So this theory explains the specific heat capacity of materials. This theory explains the specific heat capacity of a materials. The second merit is this theory explains photoelectric effect, Compton effect and black body radiation. And this theory gives the correct mathematical expression for the thermal conductivity of metals. Thermal conductivity of metals. What are the drawbacks of quantum free electron theory is this theory is failed to distinguish between the metals, semiconductor and the insulators. It is also failed to explain the positive value of Hall coefficient. And also according to this theory, only 2 electrons present in the Fermi level and they are responsible for the conduction, which is not true. These are the drawbacks from the quantum free electron theory. So what are the statistics? So what are the statistics we are going to explain? So in this we know that three statistics are there: Maxwell-Boltzmann statistics, Bose-Einstein statistics, Fermi-Dirac statistics. In this we are going to concentrate on the Fermi-Dirac statistics or Fermi-Dirac distribution function. In this we are going to discuss about the Fermi energy also. So what are the statistics here? So let us consider three statistics: MB statistics, BE statistics, FD statistics. MB statistics means Maxwell-Boltzmann statistics. According to the what is Fermi energy? What is Fermi energy? So F of E is equal, so we can consider the Fermi energy F of E, that is equals to 1 by e power h in u by kt. That is a Fermi distribution function. So according to that, so it deals in that Maxwell-Boltzmann statistics, these particles deals with these particles, the electrons are with particles which has no spins. So this Fermi-Dirac Maxwell, according to Maxwell-Boltzmann statistics, which are deals with the particles which has no spin. So examples of these particles is gaseous particles. So the second is Bose-Einstein statistics. So the Fermi-Dirac distribution function F of E is equals to 1 by e power h in u by kt minus 1. So this, according to this BE statistics, it deals with the particles which has integral spin. So these particles we can known as a bosons. So examples from for the Bose-Einstein statistics is photon and gluons and helium atoms. So what is Fermi-Dirac statistics? So when we consider the Fermi-Dirac distribution function F of E is equals to 1 by e power h in u by kt plus 1. So it deals with the particles with a half integral spin. Also known as, these particles is also known as fermions. So what are the example for this? Electron, protons, neutrons, quarks and neutrinos. So what is Fermi level? What is Fermi energy? The earlier slide we consider Fermi energy F of E. So we can that level which consisting of energy, that is a Fermi energy. So we can consider F of E is the Fermi level of having some energy, that is Fermi energy. So what is Fermi level? What is Fermi energy? The energy of the highest occupied level at 0 degree absolute temperature. 0 degree absolute temperature is called Fermi energy, and the energy level is referred to as the Fermi level. The Fermi energy is denoted by EF. Means here what is Fermi level? What is Fermi energy? Means what is Fermi level is nothing but the energy of the highest occupied energy level is called Fermi energy level at absolute temperature. At absolute temperature is called Fermi energy. Absolute temperature is called Fermi level. So that level which consisting of some energy is called Fermi energy. So that energy is Fermi energy which is denoted by EF. So as we know that for any metal containing suppose n atoms, if you consider any metal, it consisting of n atom, capital N atoms, there will be a number of energy level in each band. There will be a n number of energy level of each band. According to Pauli's exclusion principle, each energy level can occupy or can accommodate a maximum of 2 electrons, one with spin up and plus off, and other with spin down, that is minus off. So at absolute zero temperature, 2 electrons, at absolute temperature, 2 electrons with opposite spin, okay, 2 electrons with opposite spin will occupy lowest available energy levels. The next 2 electrons with opposite spin will occupy the another next energy levels, and so on. So if the level, whatever the energy level, the state which consisting of 2 energy levels with opposite spin, and then 2 energy levels which the level which consisting of another 2 electrons with opposite spin, like that goes on. So up to what energy level, up to what highest energy level which is occupied by the electron with opposite spin is called Fermi level. That is Fermi level. This Fermi level which has some energy, that is Fermi energy. Fermi energy. So the topmost energy level occupied by electron at absolute temperature is called Fermi energy level. The energy corresponding to that energy level is called Fermi energy. So here it is very clear about the Fermi level. So initially the two electrons in each energy level, each level which consisting of two electrons with opposite spin, the next level which consisting of two electrons with opposite spin, and so on. It occupies the almost is a maximum level, that is topmost energy level, so which consisting of the electrons with opposite spin. That topmost energy level is called Fermi energy level. This is Fermi energy level. So this Fermi energy level corresponding some energy, that is Fermi energy. So here when we observe this Fermi energy diagram, this is an electron energy. So here we are classification of the solids, metal, semiconductor and the insulators. So if you are observe here the metal, so in these two bands in between this Fermi energy level, this is a Fermi energy level. So this Fermi level. So if you consider the metal or semiconductor or insulator, so we have two bands. We know that the lowest band is the valency band, highest band is the conduction band. Lower band is valency band, upper band is conduction band. In between the Fermi level will be occupied. So if you take the semiconductor, the Fermi energy, the Fermi level which is occupied in between the valency band and the conduction band. So here also valency band and the conduction band. In these metals, the valency band and the conduction band overlap each other, and the semiconductor valency band and the conduction band has some energy band, that is band gap. So and also coming to the insulator, the valency band and the conduction band having some energy band gap is more compared to the semiconductor. So that is the insulator. So the Fermi level which is lies between the in between conduction band and the valence band. So next, all energy levels below the Fermi level are completely filled, and above which all energy levels are completely empty. So let us consider the Fermi energy level. This is a valency band, this is a valency band, this is a conduction band. So here what they are saying, all energy levels, suppose it is considered this is a Fermi level. So in this a Fermi level, this all energy levels below the Fermi level which is occupied, completely occupied. Above the Fermi level which is completely empty. So at above absolute temperature, this is where at temperature at T is equals to 0. At T is equals to 0, at T equals to 0, this is the Fermi level. So below that is completely filled. This is completely empty. When at T is equals to completely empty. So at T is equals to 0 degrees Kelvin. So at temperature above the absolute temperature, the electrons get thermally excited. And move up to the higher energy level. As a result, there will be many vacant energies levels below as well as above Fermi energy level. So at 0 degrees temperature, at absolute 0 degrees temperature, so the Fermi level, we know the Fermi level which is occupied in between the valency band and the conduction band. So in this Fermi level, so whatever the below the Fermi levels energy levels are available, so in this the electrons which are occupied by the energy levels, electrons are occupied by the energy levels below the Fermi level which is completely filled. Above the Fermi level is completely empty. Okay, at 0 degrees temperature. So when we increasing the temperature means as the temperature above the absolute zero, the electrons get thermally excited. So the electron get thermally excited, move from the lower band to the highest band, lower band to the below to the upper, means higher energy levels. So as there is many vacant energy levels below and the above Fermi level. So temperature will increase whatever the electrons which are thermally excited and move from the lower band to the higher band. So means the Fermi level in between the lowest band and highest band. So means when the electron move from the lower band to the higher band, so here some vacants are available here. So at the same time, all electrons are not move from the lower band to the higher band. Some of the electrons are which are staying in the lowest band. So some of the vacant is created in this lowest band, and some of the empty energy levels are available in the higher band. So under thermal equilibrium, the distribution of the electrons among various energy level is given by the statistic function. So when we are taking the thermal equilibrium, so we are considering where the electrons are available, where the electrons are available and how many states are available, how many states are occupied by the electrons. That is given by some function, that is the statistical function, that is F. So the function F of E is called Fermi factor or Fermi-Dirac distribution function. So the function, whatever the statistical function, we can call it as a Fermi factor or Fermi-Dirac distribution function, and this gives the probability of the occupation of a given energy level under the thermal equilibrium. What is Fermi-Dirac distribution function? Means the probability of occupation of the energy levels at thermal equilibrium. So what is Fermi-Dirac distribution function? So this expression for the Fermi-Dirac distribution function F of E is equals to, so the Fermi-Dirac distribution, this probability of a function is a mathematical representation of the probability of distribution of the energies of the quantum state that electron can exist in at some given temperature. So it describes what happens to the electron inside the metal solids as the temperature of the solids is increased. So here this is a mathematical expression. The Fermi-Dirac probability is a function of a mathematical expression which gives the probability of the distribution of energies in a quantum states. And when the temperature is increased, what happens in the electrons inside the metal? So we are taking the equation, that is F of E is equals to 1 by 1 plus e power E minus EF by kBT. So what is F of E here? We already discussed the Fermi-Dirac distribution function or Fermi factor. So EF is the Fermi energy. And F of E is the Fermi-Dirac distribution function, and K is the Boltzmann constant. T is the temperature of metal under thermal equilibrium. T is the temperature of metal under thermal equilibrium. So according to that, we can write some points from the Fermi-Dirac distribution function. So the Fermi-Dirac distribution function F of E is used to calculate the probability of an electron occupying a certain energy level. So what is F of E? Here it is used to calculate the probability of the electron which are occupying in the certain energy level. So the distribution of electrons among the different energy levels as a function of temperature is known as Fermi-Dirac distribution function. So what is the Fermi level and the Fermi-Dirac distribution function? So we can consider as a metal, there is one partially filled band which is results of conduction band overlapping with the valency band. So let us consider a metal, so which is in this one partially filled, so that is conduction band. and also completely filled by the valency band, completely filled by the electrons in the valency band, so partially filled by the electrons in the conduction band. So in the first band is lowest band is called valency band. The lowest energy levels are first filled. This valency band filled by the electrons is first they are filled. So the highest occupied energy levels at absolute temperature is called Fermi level. So and the energy corresponding to it's called Fermi energy, that is denoted by F. So what they are trying to say this, in this metal there is one partially filled band is which is conduction band, and that conduction band overlap with the valency band. So in this band the lowest energy levels are first filled, and then when we increasing the temperature, the electrons are thermally excited that move from the valency band to the conduction band. Whatever the highest occupied energy level is called Fermi level. That Fermi level which has some energy, that is the Fermi energy. So that is T is equals to 0, and then T is greater than 0 degrees. What happens? The distribution of the electrons over a range of allowed energy levels at thermal equilibrium is given by the Fermi-Dirac distribution function, that is 1 by f of E is equals to 1 by 1 plus e power EF minus EF by kT. F of E is the probability of occupancy of electron in the energy level C. EF is the Fermi energy. T is the absolute temperature in 0 degrees Kelvin, and the K is some value that is 1.38 into 10 to the power of minus 23 joule per Kelvin. So here we are increasing the temperature. This is at absolute temperature, and also increasing the temperature. And what is the Fermi-Dirac distribution function with different Fermi-Dirac distribution function values and the Fermi energy. So this energy values is the Fermi-Dirac distribution function. What happens when the energy is increased? What about the Fermi-Dirac distribution function? So what is the equation for the Fermi-Dirac distribution function is Phi is equals to 1 by 1 plus e power E minus EF by kT. So at 0, this energy. So here E is less than EF, one condition, and E is equals to EF. E is greater than EF. What happens? Three conditions. This is the E is less than EF. This is the E is equals to EF. This is the region is E is greater than EF. So what is Fermi-Dirac distribution function? At E is less than EF, it has some maximum Fermi-Dirac distribution value is 1, maximum value. When it is increased, when the energy is increased, the Fermi level which is lies at E is equals to 0, this is a 1 value. So then E is greater than EF, it comes to the decreases. So when we are taking the values corresponding E is less than EF, E is equals to EF, E is greater than EF. What about the Fermi-Dirac distribution function? Let us calculate by the mathematical expression. By using this mathematical expression, let us calculate the what is happened when the Fermi energy is function. What happens when we increasing the Fermi level, which is energy is less than Fermi level energy. Energy is equals to Fermi energy, and the energy is greater than the Fermi energy. So let us consider Fermi-Dirac distribution function f of E is equals to 1 by 1 plus e power E minus EF by kT. So at T is equals to 0. Here that T is equals to 0. And the energy E is less than EF in the first case. E is less than EF in the first case. So E minus, first let us take the value E minus EF by kT. Here T is equals to 0. E minus EF minus E is less than EF. E is very less. So automatically EF is greater value. So EF is having a negative value, so that we get the minus negative number by T is a 0. Minus negative number by 0, something by 0 infinity, minus something something by infinity, minus something by 0 is a minus infinity. So we can write a minus 1 by exponential minus e power minus infinity, we can write as e power infinity. 1 by infinity we can write as 1 by infinity. So let us get 0 value. So when T is equals to 0, E is less than 0, E is less than EF, the Fermi-Dirac distribution function f of E is equals to 0. So means this is the e power E minus EF by kT. So then this value 0 value we have to substitute in this Fermi-Dirac distribution function. 1 by 1 plus 0. 1 plus 0 is a 1. 1 value is 1 by 1 is a 1 value. 1 value. So this is the Fermi-Dirac distribution function when T is equals to 0, E is less than EF. So this indicates all energy levels EF are completely filled at absolute 0 temperature. E1 means completely filled. 0 means completely empty. Completely empty. Some value will be there, some value that is partially filled. So let us take the second case. T is equals to 0, E is greater than EF. So what happens? E is greater than EF. E value will be more. So this value will be very small. So then the positive value by T is a 0. So 0. So e power infinity equals to infinity. This infinity we can substitute in this equation. 1 by 1 plus infinity. We can add any number to the infinity, we will get the infinity. Something by infinity we can write it as 0. So T equals to 0, E is less than EF, we will get the value Fermi-Dirac distribution function is 0. Means E is greater than E means 0. Here 0. So then before the E is less than EF, so we will get the value Fermi-Dirac distribution value 1. So that is value 0 value. So what about the another case, that is T is equals to 0, T is equals to EF. T is equals to 0, E is equals to EF. What about the Fermi-Dirac distribution function? So that is, so this is E is less than EF, E is greater than EF, this is E is equals to EF. So E is equals to EF, so E is equals to EF here, E equals to EF is, that is equals to 0, plus EF minus EF 0 by K into T is a 0, so 0 and a 0. 0 by 0, e power 0 by 0 is not defined value. So Fermi-Dirac distribution function cannot give us probability of occupancy at 0 degrees Kelvin. The Fermi energy is equals to the energy of the electron, which is gives to the Fermi energy level. So if you are finding the probability of the function f of e, we can't define the probability of the electron where it is occupied exactly. So this is the graph between the E and Fermi-Dirac distribution function and the Fermi level. So what are the conclusions? What is the importance of the Fermi energy? Fermi energy level is used to separate the vacant and filled state at 0 degrees Kelvin. We know that Fermi energy level, this is Fermi energy level. So which is lies between the valency band and the conduction band. So which gives the valency band at 0 degrees Kelvin, which is completely filled. It is completely empty at T is equals to 0 degrees. So what they are saying, the Fermi energy level used to separate the vacant and the filled state. So this is one point. It is used to know the status of the electron. It is used to status of the electron, where the electron is exactly occupied in that energy level. Electrons are completely filled below the Fermi energy level and completely empty above the Fermi level at 0 degrees. Already we discussed when we separate the Fermi energy level. So below the Fermi energy level, that is completely filled, and above the Fermi level it is completely empty at 0 degrees Kelvin. At above 0 degrees, some electrons absorb the thermal energy and then get excited to the lower energy states, to the higher energy levels or higher energy states. This is the importance of the Fermi level, and the Fermi level which consisting the some energy, that is Fermi energy. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.